This is Ross Kendall. This is my first update for my project titled The Joule Effect Heating of a 1045 Steel Sample. So the first thing I did this week was I went through the 3 references that were provided to me in Blackboard. This first one was slides made by Ernesto that specifically in here, the one that caught my eye was a 2D model involving the quenching of a piece of anything really. The second one here was a paper written about the Joule effect heating of nanowires, which was good. It sent me, and I'll show you where it sent me for the first thing I did for the project. And I also looked at this third. This is a ComSol program. This dealt with cylinders, so it was useful to start. I'll probably use that later on, but let's see what I got so far. So that paper, it led me to this general heat equation, right? You have a change in temperature with respect to time, and there's a positional term here, and then there's a heat generation term here. If you assume that the current going through the piece of steel is all constant across the whole piece of steel, then that positional term could get canceled out, and you're just left with this heat generation term, which is just equal to the current coming in times the voltage, or the current squared times the resistance of the steel. So I basically wanted to use this equation to figure out exactly how fast the steel can heat up if a certain current is applied to it or across it. So the next thing I had to do was I had to find a bunch of values for the steel. This is a table that basically summarizes the properties that I would use. And there's also some heat transfer coefficients that I needed for the ComSol model, so I had to find those too. So, but using these terms here, I was able to solve for the maximum change in temperature with respect to time, and that was equal to 261.45 Kelvin per second based on a 10 to the 9th amount of watts entering the piece of steel. So I needed to confirm that this analytical solution would be equal to a numerical solution. This is a very simple program. So I built a 1 by 1 by 1 cube in ComSol, and I created a heat source that goes across the whole cube equal to 10 to the 9th. And then I assumed that all the boundaries were insulated so that all the heat is contained within the block. Nothing leaves the side. So I ran this guy, and I ended up with a cube that was all the same temperature, which makes sense, and it changes with respect to time. Let me show you that here. So this number changes. So I made a line graph basically plotting out the change in temperature with respect to time, and then I took these values out and made a table, and it is shown here. So basically in each step you go forward a second, you get a increase in change in time, a linear step here, and this 261.45 equals exactly what I got. So I know that at least I'm working with the right equation, and that my analytical solution is equal to my numerical solution. The next step will be to make more reasonable boundary conditions. So I'm going to start with the flat plate, and rather than having each one of these boundary conditions insulated, they're going to all have natural boundary conditions. And then the goal of this is to show that the temperature in the center of the plate is obviously going to be somewhere near maximum, and that on the walls of these you have temperatures that are slightly lower. So that's my plan going forward, but I feel like I've made a good progress this week, and look forward to figuring out what I'm going to do next week. Thanks.